Now in this lecture we'll answer on two questions. In the first question we will find out the radius of this circle that is inscribed by the right triangle ABC. And in the second question we will find out the area of the blue right triangle BCD, that is inscribed by this quarter circle. Okay, so we start with the first question. In the drawing we have a right triangle ABC. Know that side AB equals to 90 degrees. Angle ABC equals, side AB equals to 8 units. Angle ABC equals to 90 degrees. Inside this right triangle we have this circle that is inscribed by the right triangle ABC, and we want to find out the radius of this circle that is inscribed by triangle ABC. So first of all we will define, and we also know it is given us the question that the length of side BC and the length of the hypotenuse AC are integers. Okay, and we want to find out the radius of this circle. So first of all we will define the length of side BC of the right triangle ABC as A. So here BC equals to A units according to our definition, and we define the hypotenuse AC. The length of the hypotenuse AC will be equal to B units according to our definition. Okay, here the hypotenuse AC, it will be equal to B units according to our definition. And it is given us the question that AB equals to 8 units. So now we will implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in the right triangle ABC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is the relation for Pythagoras theorem. In the right triangle ABC, you can write down that the square of the hypotenuse is AC squared, and it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to AB squared plus BC squared. Okay, I repeat again that according to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. Okay, AC equals to B according to our definition. Therefore AC squared is equal to B squared. And it is equal to AB squared. AB equals to 8 units according to what is given us in the question. So AB squared is 8 squared, that is 64, plus BC squared. BC equals to A according to our definition, therefore BC squared is A squared. So in conclusion, we found out that according to equation number 1, B squared equals to 64 plus A squared. Here we subtract A squared from this equation number 1, and we get that according to equation number 1, B squared minus A squared equals to 64. Okay, B squared minus A squared equals to 64. we use the algebraic identity that states that b squared minus a squared is actually equals to b plus a times b minus a, and it is equal to 64. Okay, so actually it is given us the question that here AC and BC are integers, and that is to say AC equals to B and BC equals to A, so B and A are integers according to what is given as the question. That is the first thing that we know from the question, that A and B are integers. And the second thing is that we know that A and B are the lengths of the right triangle, so A and B, they are lengths, and as the lengths, they must be positive numbers. Okay, they must be a positive. So in conclusion, we derive from 1 and 2 that A and B are positive integers. A and B are positive integers. And actually, all the positive integers, they are the natural numbers. So, here, we know that B is a positive integer and A is also a positive integer. Therefore, B plus A will be also a positive integer. But B plus A must be greater than B minus A because of the simple fact that when you add two positive integers to each other, the result must be greater than the situation that you subtract the two integers numbers from each other. So B minus A is greater than B plus A is greater than B minus A, and here B is the hypotenuse and A is perpendicular, so B must be greater than A because the hypotenuse must be greater than the perpendicular, so B is greater than A. Here we subtract from this inequality A, and we get that B minus A equals to, is greater than 0. So if B is a positive integer, A is a positive integer, and B minus A is also positive, it means that B minus A must be also a positive integer. So B minus A is also a positive integer, because when you subtract two positive integers from each other, if the result is not the negative number but a positive number, it must be a positive integer. Okay? When you add two positive integers to each other, the result must be a positive integer. And when you subtract two positive integers from each other, the result also must be a positive integer. If you know from the beginning that the result is not negative, so the result must be a positive integer, we will not discuss on the situation that if a equals to b, of course the result is 0, but if a is not equals to b, then and b minus a is a positive, so b minus a must be a positive integer. Okay, so actually, according to equation number 1, we know that b plus a times b minus a equals to 64. That is to say, we multiply two positive integers by each other, and the result is 64. So there are not a lot of possibilities that we will have here to multiply two positive integers by each other and get the result of 64. So we'll write down all the possibilities of two positive integers. If we multiply them by each other, will give us 64. So what are all the possibilities? Actually, here b plus a could be 1 and b minus a could be 64. 1 times 64 is 64. The second possibility is that b plus a will be equal to 2, and the result and b minus a will be equal to 32. 2 times 32 is 64. The third possibility is that b minus a equals to 4, b minus a equals to 16, and 4 times 16 is also 64. And then b plus a could be 8, b minus a could be also 8, and 8 times 8 is also 64. And then we have also the possibility that b plus a equals to 16. So b minus a will be equal to 4, and 16 times 4 is 64. And we also have the possibility that b plus a equals to 32, b minus a equals to 2, and 32 times 2 is 64. And the last possibility is that b plus a equals to 64, b minus a equals to 1, and 64 times 1 is also 64. So we have here 7 possibilities for the values of b plus a and b minus a. Okay, but because of the fact that b plus a is greater than b minus a, it means that here we have two columns, and the first column must be greater than the second column, because b plus a is greater than b minus a. So only and only if b plus a equals to is greater than b minus a, it will be a valid option. Otherwise, we'll cancel this possibility, because b plus a must be greater than b minus a. 1 is not greater than 64, so we'll cancel this possibility. 2 is not greater than 32, therefore we'll cancel this possibility. 4 is not greater than 16, so we'll cancel this possibility. 8 is not greater than 8, so we'll cancel this possibility. 16 is greater than 4, therefore this possibility is an option of the solution to the question. 32 is also greater than 2, so this is also a good possibility for the solution of the question. And we also know that 64 is greater than 1, so this is also possibility for the solution of the question. In the next step, we will add the two numbers together and we will see what is the result. So b plus a, this is the first number, we will add the first number to the second number, that is b minus a. So what is the result of b plus a? plus b minus a. B plus b is 2b, and a minus a is 0. So in conclusion, we got to the result that if we add the two numbers together, the result must be an even number. 2b is even number because of the fact that b is a positive integer, therefore 2b must be an even number. So we take into account as the solution to the question only all the possibilities that if we add the two numbers together, we will get only an even number, and if we get odd number, it is not a good solution to our question, because when we add the two numbers together, we have to get an even number. So we check in which is the possibilities that by adding the two numbers together, we get an even number. 16 plus 4 is 20. 20 is an even number, therefore this is a good possibility for the solution of the question. 32 plus 2 is 34. This is also a good possibility for the solution of the question. While 64 plus 1 is 65. 65 is an odd number, it's not an even number, so we cancel this possibility. So we left only with two solutions that are possible for the question. That b plus a equals to 16 and b minus a equals to 4. And the second possibility is b plus a equals to 32 and b minus a equals to 2. Okay, and so we write them down. So according to the first solution to the question, we found out that b plus a equals to 16, while b minus a equals to 4. This is the first solution that are possible. And the second solution that is possible to the question is that b plus a equals to 32 and b minus a equals to 2. Okay, those are the two possible solutions to the question. In the next step, we will find out the values of a and b in each possibility. We have two possibilities here. In order to find out the value of a and b, in the first possibility, we will add equation number 1 to equation number 2. b plus b is 2b, a minus a is 0, and 16 plus 4 is 20. So in conclusion, we found out that 2b equals to 20. Here we'll divide this equation by 2, and we'll get that the value of b is 20 over 2, that is 10 units. B equals to 10 units, that is to say, the hypotenuse b equals to 10 units, according to the first solution. And what is the value of a? Here we know that b plus a equals to 16 units. We'll subtract b from this equation and we'll get that a equals to 16 minus b. So we found out that a equals to 16 minus b. And we have already found out that b equals to 10 units. So we substitute b by 10 units and we get that a equals to 16 minus b, and b is 10, so 16 minus 10. So a equals to 16 minus 10, that is 6. So in conclusion, we found out that according to the first solution to the question, is that a, the perpendicular a here this is a, it is equal to 6 units, while the hypotenuse AC that is equal to b, it is equal to 10 units. That is the first solution to the question. Now we'll find out A and B for the second solution by adding the first equation to the second equation. B plus B is 2B, A minus A is 0, and 32 plus 2 is 34. So in conclusion, we found out that 2B equals to 34. We will divide this equation by 2, and we'll get that B equals to 34 over 2 is 17 units. So the hypotenuse, according to the second solution to the question, is the hypotenuse B equals to 17 units. And what is the value of A? According to this equation, B plus A equals to 32. We subtract B from this equation and we will get that A equals to 32 minus B. That is to say, we have already found out that B equals to 17, so A equals to 32 minus B, that is 17, and 32 minus 17 is 15. So we found out that A equals to 17 units, and B 32 minus 17 is 15. 32 minus 17 is 15, so A equals to 15 units, and B, the hypotenuse B, equals to 17 units. In the next step, I will draw the two right triangles here, and we will see what we have to find more than A and B. Actually, the question was not to find out the values of A and B, but to find out the radius of the circle that is inscribed by triangle ABC. Okay, so we didn't finish yet the question. We have a lot of work to do. So here we have the right triangle, triangle ABC. In the right triangle, triangle ABC, according to the first solution, the hypotenuse equals to 10 units, that is B. It is given as the equation that AB equals to 8 units, and BC, that is A, equals to 6 units. This is a right angle. Actually, inside this right triangle, we have this circle that is inscribed by this right triangle, triangle ABC, and the question here is to find out the radius of this circle that is inscribed by this triangle, triangle ABC. So we define the center of this circle is O, and we define the radius of this circle as capital R. So our mission is to find out the value of capital R in this right triangle. This is the first solution, the first possible for the solution of the question, but we have also another triangle. We have the second triangle, triangle ABC. In this right triangle, triangle ABC, we know that the hypotenuse AC equals to 17 units. We also know that the perpendicular BC equals to 15 units, and it is given as the question that AB equals to 8 units. Inside this right triangle, triangle ABC, we have a circle that is inscribed by this triangle, and our mission is to find out the radius of this circle. This is the circle that is inscribed by the right triangle, triangle ABC. And the center of this circle is at point O, and the radius of this circle is capital R, and our mission was to find out the value of capital R, that is the radius of this circle. Okay, so in order to find out the radius of the circles that are inscribed by those two right triangles, we'll take triangle ABC, that could be any triangle. Here, this triangle ABC, could be any triangle. Inside this triangle ABC, we have this circle that is inscribed by this triangle ABC. And we find out the radius of this circle. And then we will implement the formula that we found here for the radius of this circle in our specific two right triangles. So triangle ABC could be any triangle, therefore the length of side AB is equal to A units, or AB equals to A units in its length. Side BC equals to B units in its length. And side AC, the hypotenuse AC, equals to C units in its length. Okay. Our mission is to find out the radius of this circle that is inscribed by this triangle, triangle ABC, that could be any triangle, any right triangle, of course. It could be any right triangle, because this is a right triangle. So the formula that we will find will be good only for right triangles, for a circle that is inscribed in a right triangle only, and not in every triangle. Okay? So here we define the center of this circle as O. We define the point of tendency of tangent BC with this circle as N. So capital R is the radius of this circle. We define the point of tendency of tangent AB with this circle as M. In the next step, we will join points O and M together by a straight line. Here, point O is the center of the circle. Point M is the point of the circle itself. This is exactly the definition of a radius. That is to say, line segment OM is the radius of this circle that is equal to capital R according to our definition. So here we have rule number 1 that says that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here the radius OM, it is drawn to the point of tendency, therefore tangent AB will be perpendicular to the radius MO according to rule number 1. See? So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we have here the radius ON that is drawn to the point of tendency. That is to say, the radius ON, it is drawn to point N, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1, of course. So actually, in quadrilateral MOBN, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, this is actually angle MON. In total, the sum of those four angles must be equal to 360 degrees. So 270 degrees plus the size of angle MON must be equal to 360 degrees. If we subtract 270 degrees from the equation, then the missing angle MON will be equal to 90 degrees. So we found out that the missing angle is the right angle, it is equal to 90 degrees. Actually, we found out that in quadrilateral MOBN we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So, and therefore quadrilateral MOBN is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, MO equals to BN. MO equals to BN, but we know that MO equals to R. Therefore, BN that is equal to MO will be also equal to R, to capital R. Likewise, we know that according to the rule that the opposite sides of a rectangle are equal to each other, we get that MB equals to ON. MB equals to ON, but ON equals to R. ON equals to R, and we know that MB equals to ON, therefore MB will be also equal to capital R. So after we found out that all the sides of quadrilateral MOBN are equal to each other, they are equal to R. Therefore, quadrilateral MOBN, it is not a rectangle, but a square. In the next step, we find out the length of line segment AM. Here, from the drawing, it is very easy to see that AM equals to AB minus MB. So AB is A minus MB is R, capital R. So in conclusion, we found out that the length of line segment AM equals to A minus R. Likewise, we find out the length of line segment NC. It is very easy to see from the drawing that NC equals to BC minus BN. BC is B minus BN is capital R. So in conclusion, we found out that NC equals to B minus capital R. In the next step, I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. I repeat again, the lengths of two tangents from a common external point to a circle are equal. So we will focus on the common external point, point A. From the common external point, point A, we have two tangents to this circle. We have tangent AM and tangent here. We will define the point of tendency of tangent AC with this circle as L. So the second tangent to this circle is tangent AL. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, AM equals to AL according to rule number 2. AM equals to AL for one side, but we know also that AM equals to A minus R. And AM equals to AL, therefore AL will be also equal to A minus R. So in conclusion, we found out that AL equals to A minus R. Likewise, if we focus on the common external point, point C, from the common external point, point C, we have two tangents to this circle. We have tangent CL and tangent CN. And according to rule number 2, they are equal to each other. That is to say, CN equals to CL according to rule number 2. But we have already found out that CN equals to B minus R. And CL equals to CN. Therefore, CL will be also equal to B minus R. Here CL also equals to B minus R. So in conclusion, we found out that CL equals to B minus R and AN equals to A minus R. So what is the length of the hypotenuse AC? The length of the hypotenuse AC, it is equal to from the drawing, it is very easy to see that AC equals to AL plus LC. AC equals to AL plus LC. And again, AC equals to AL plus LC. Okay. So the hypotenuse AC equals to AL is A minus R. AL is A minus R, plus LC is B minus R. So in conclusion, I found out that the hypotenuse AC equals to A minus R plus B minus R. But according to our definition, AC equals to C. So we substitute AC by C, and we get that C equals to A minus R plus B minus R. So C equals to A plus B, minus R plus minus R is minus 2R. So in conclusion, we found out that C equals to A plus B minus 2R. We will add 2R to this equation, and we'll get that 2R plus C equals to A plus B. Okay, we'll subtract C from this equation, and we'll get that 2R equals to A plus B minus C. Here we'll divide this equation by 2, and we'll get that R, that is the radius of the circle that is described by triangle ABC, that could be any right triangle. It is equal to A plus B, that is the sum of its perpendiculars, minus C, that is minus the hypotenuse, over 2. So actually we found here a general formula that will help us to find out the radius of any right triangle that blocks a circle, or the radius of any circle, the radius of any circle that is inscribed by right triangle, triangle ABC, that could be any triangle. Okay? This is a new formula that will help us to find out the radius of a circle that is inscribed by any right triangle, triangle ABC. So we can implement the new formula in our drawing in our two right triangles. The new formula is R equals to A plus B minus C over 2. A plus B is the sum of its perpendiculars, that is 8 plus 6, minus the hypotenuse, that is 10 over 2. So R, the radius of this circle that is described by this triangle, triangle ABC, equals to 8 plus 6 is 14, 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle is equal to 2 units. So R here equals to 2 units. This is the first possibility for the solution of the question. And the second possibility for the solution of this question is that the radius of this circle that is inscribed by this specific right triangle, triangle ABC, will be equal to the sum of its perpendiculars, that is A plus B, is 8 plus 15, minus the hypotenuse, that is 17, over 2. So here 8 plus 15 is 23, and 23 minus 17 over 2. So 23 minus 17 is 6, and 6 over 2 is 3. So we found out that the radius of this circle that is described by this specific triangle, triangle ABC, equals to 3 units. And the radius of this circle that is described by this triangle is 2 units. So actually the solution to the question is that we have two solutions to this question. The radius of this circle that is described by this right triangle, triangle ABC, could be equal to either 2 units or to 3 units. And this is the answer to this question. So we finished with the first question. In the next step, I present to you the second question, and we will solve the second question in 2 different methods. Okay? So here, so already mentioned, the radius of this circle will be equal to either 2 units or 3 units. Okay? So we start with the second question. In the domain, we have a quarter circle AOB. We know that side OB equals to 2 units, OD equals to AD. Inside this quarter circle, we have right triangle, triangle DCB. Angle BCD equals to 90 degrees, and we want to find out the area of this right blue triangle, triangle BCD. We start with the first method. First of all, angle AOB equals to 90 degrees because of the fact that we are talking about a quarter circle, therefore this angle must be equal to 90 degrees. Also, O is the center of the quarter circle. Point O is the center of the quarter circle. And we also know that OB is the radius of the quarter circle, and OA is also the radius of the quarter circle. And we also know that AD equals to DO according to what is given us the question. So in conclusion, we can write down that AO equals to OB, AO equals to OB, and they are both the radii of the quarter circle. This is the radius of the quarter circle that is equal to 2 units. But according to what is given us the question, we know that AO equals to AD plus DO. AO equals to AD plus DO. And here, according to what is given us the question, AD equals to DO. So if we define AD as X, then DO will be also equal to X. So AD plus DO is X plus X. X plus X is 2X, and according to this equation, 2X equals to 2. Here we divide this equation by 2, and we get that X equals to 2 over 2, that is 1. X equals to 1, so here AD equals to X equals to 1 unit. DO is also equals to X, that is equal to 1 unit. Okay? In the next step, we complete the quarter circle to a circle. And we'll extend the radius BO by a straight line until it touches the circle. We'll define the touching point of the extended BO in the circle as point P. So actually, O is the center of the circle and also the center of the quarter circle. P is a point on the circle itself. This is exactly the definition of a radius. That is to say, PO is the radius of this circle, that is equal to 2 units according to what is given as the question, because the radius of the circle is the same radius that is also the radius of the quarter circle. Okay? So here, from point D, actually we will extend side CD by a straight line until it touches the circle. But we don't know at which points the extended side CD will touch the circle. So we suppose that the extended line segment CD will touch the circle at this point, that is point X. Okay, so according to our assumption, when we extend the straight line CD by straight line, when we extend side CD by straight line, it will touch the circle at point X. Actually, we created here peripheral angle BCX. I write it down. We actually created peripheral angle BCX and peripheral angle BCX peripheral angle BCX according to what is given as the question, peripheral angle BCX equals to 90 degrees. It is given as the question. So we actually found out that we have peripheral angle BCX that is equal to 90 degrees. And it touches the circle at point X. But here we'll get a contradiction because of the fact that we have the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Here the diameter of this circle is PB. Why PB is the diameter of the circle? Because it passes from point O. We extended the radius BO by straight line, so PB is a straight line, or it is a chord that passes from point O, that is the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. So PB is the diameter of the circle, and according to the rule that I mentioned, that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. It means that peripheral angle BCX must rest on PB. Okay, but here peripheral angle BCX doesn't rest on PB, but it is rest on BX. This is a contradiction to the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter that is PB. Therefore, in order to avoid the contradiction, we must conclude that point X merge with point P. And actually here, when we extend the straight line CD, side CD by straight line, it will touch the circle only at point P. It will touch the circle at point B, and in this way we'll get that this peripheral angle BCP that is equal to 90 degrees indeed rests on the diameter that is PB. Otherwise, we'll get the contradiction. We'll get here peripheral angle that is equal to 90 degrees and it doesn't rest on the diameter. In order to avoid the contradiction, we must conclude that the side CD with extended CD must touch point P. When it touches the circle only and only at point P. Okay, so here we have PB is a straight line because it is diameter, and diameter, it is absolutely a straight line. PB is a straight line, and we know that the sum of the angles on one side of a straight line equals to 180 degrees. So if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees. So this angle equals to 90 degrees, plus the size of this angle and this angle AOP. In total, they must be equal to 180 degrees according to the rule that I mentioned. So if we subtract from the equation 90 degrees, we will get that this, the missing angle AOP must be equal to 90 degrees. This is a right angle. Therefore, we created here right triangle POD. We'll find out the diameter of the hypotenuse of the right triangle, triangle PD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here in the right triangle, triangle POD, in the right triangle, triangle POD, by PT is by Pythagoras theorem, we get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say the hypotenuse is PD, so the square of the hypotenuse is PD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say it is equal to DO squared plus PO squared. Okay? So PD squared equals to DO squared. DO is 1, so DO squared is 1 squared, that is 1, plus PO squared. PO is 2, so PO squared is 2 squared, that is 4. So in conclusion, we found out that PD squared equals to 1 plus 4, that is 5. Here we take a root out of this equation, and we get that the hypotenuse PD equals to the square root of 5 units. We found out that the hypotenuse PD equals to the square root of 5 units. We repeat the same process on the right triangle, triangle DOB. In the right triangle, triangle DOB, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right triangle DOB, by PT, here the square of the hypotenuse is DB squared. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DO squared plus OB squared. Okay, so actually I found out that DB squared, that is the square of the hypotenuse, DB squared equals to DO squared. DO is 1, so DO squared is 1 squared, that is 1, plus OB squared. OB is 2, so OB squared is 2 squared, that is 4. So in conclusion, we found out that PB squared equals to 1 plus 4, that is 5. We will take a root out of this equation, and we will get that the hypotenuse PB equals to the square root of 5 units, exactly like PD. The hypotenuse PD equals to the square root of 5 units. Okay, in the next step we will extend the radius AO by a straight line until it touches the circle. At this point, we define the touching point of the extended AO and the circle is point Z. And I will present to you rule number 1. I will present to you rule number 1. According to rule number 1, rule number 1 deals with two chords that intersect with each other inside the circle. So here we have two chords. We have this circle first of all. This is rule number 1. So we have here this circle, inside this circle we have two chords. We have here chord AB, this is chord AB, that intersects with chord CD, this is chord CD, at point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Actually, we can implement rule number 1 in our drawing. Why? Because in our drawing we have chord AZ, chord AZ. This chord intersects with chord CP, and the intersection point of chord AZ with chord CP is at point D. Okay, this is point D, the intersection point. Therefore, we get that according to rule number 1, AD times DZ must be equal to CD times DP. Okay, this is true according to rule number 1, of course. I'll repeat again. Chord AZ intersects with chord CP at point D, therefore according to rule number 1 we get that AD times DZ equals to CD times DP. Here AD equals to 1, DZ, so here we find out the value of OZ, line segment OZ. Point O is the center of the circle. Point Z is a point on the circle itself. This is exactly the definition of a radius. That is to say, OZ is the radius of the circle that is equal to 2 units. Therefore, DZ will be equal to 1 plus 2, that is 3. And it is equal to CD. CD is the missing line segment, so we leave it as it is, times DP. DP equals to the square root of 5 units. Okay? So in conclusion, we found out that 3 equals to CD times square root of 5 units. We will divide this equation by square root of 5 units. And we will get that here CD equals to square root of 5 units, 3, CD equals to 3 over square root of 5 units. Okay, we found out that CD equals to 3 over square root of 5 units. We can write here that CD equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. So according to the Pythagoras theorem, on the right blue triangle, triangle DCB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So by PT, we get that the hypotenuse is dB, therefore the square of the hypotenuse is dB squared. And it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to DC squared plus CB squared. Okay, and repeat again, according to the Pythagoras theorem, on the right triangle, triangle DCB, dB squared equals to DC squared plus CB squared. dB equals to square root of 5 units, so dB squared is square root of 5 squared, that is 5. And it is equal to DC squared. DC is 3 over square root of 5, so DC squared is 9 over 5. And here, the missing line segment is CB, so it is plus CB squared. Here we'll subtract 9/5 from this equation, and we'll get that according to this equation, 5 minus 9/5 equals to CB squared. So here we will multiply 5 by 5 and then we will divide it by 5 in order to have a common factor with this expression. 5 times 5 is 25, minus 9 over 5 equals to CB squared. Here we will take a root, but first of all, 25 minus 9 is 16 over 5 equals to CB squared. Here we take a root out of this equation and we will get that the length of side CD it is equal actually, side CB equals to the square root of 16, that is 4 over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5 units. Here, CB equals to 4 over square root of 5 units. Now it is very easy to find out the area of the blue right triangle, triangle DCB. It will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So the area of the right blue triangle, triangle DCB, will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Okay, we already found out that DC equals to 3 over square root of 5 units, times CB equals to 4 over square root of 5 units, all divided by 2. So here, in the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. Here 12 over 2 is 6, so in the numerator we have 6. And then the denominator over to the left is only 5. So the area of triangle DCB, the blue right triangle, triangle DCB, equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. Okay, so we finished with the first method. The next step I will present to you the second method. So we have already found out in the first method that angle AOB equals to 90 degrees, AD equals to 1 unit, DO equals to 1 unit. Here we will complete the quarter circle to a semicircle. We will extend the radius BO by a straight line until it touches the semicircle at this point. We define the touching point of the extended BO in the semicircle as point P. Here point O is the center of the semicircle. Point O is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, OP is the radius of this circle, that is equal to 2 units. In the next step, we will extend side CD by a straight line until it touches the circle, and it must touch the circle at point P and only at point P according to the first method. I will not repeat on it. When we extend the straight line CD by a straight line, it must touch the circle at point P. Okay. According to method 1, angle DOP is a right angle. It is equal to 90 degrees. We have already found out that PD, the hypotenuse PD, equals to the square root of 5 units, and we have already found out that the hypotenuse DB in the right angle DOB equals also to square root of 5 units. Here we will define angle DPO as theta. So if we focus on the right angle DPO, this angle equals to 90 degrees. This angle equals to theta, so this angle must be equal to 90 degrees minus theta. In order to complete the sum of the angles in this right triangle 280 degrees, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Okay? And if you focus on the right triangle PCB, this angle equals to theta, this angle equals to 90 degrees, and for the same reason, this angle must be equal to 90 degrees minus theta. For the same reason that this angle equals to 90 degrees minus theta, this angle must be also equal to 90 degrees minus theta. So in the next step we will prove that the right triangle, the right small triangle POD is similar to the right big triangle, triangle PCB. Okay? So we'll focus on the right triangle POD and the right triangle, triangle PCB. And we will prove that those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, those two angles, they are both right angles, therefore they are equal to each other. Okay, so angle POD equals to angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. Repeat again, angle POD equals to angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. And those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle POD, this angle PDO, this angle is angle PDO, equals to this angle that is actually angle CBP, and both those two angles are equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again, angle POD equals to angle CBP, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle is a common angle that belongs to both triangles, therefore this angle equals to itself. So you can write down that this angle that is actually angle DPO equals to itself, it is actually also angle CPB. And this is equal to theta according to the definition. So angle DPO equals to angle CPB equals to theta, and it is a common angle that belongs to both triangles. So we actually proved that all three angles of triangle POD can go into all three angles of triangle PCB, therefore triangle POD is similar, this is the sign of similar, to triangle PCB according to angle similarity rule. Okay? And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it also equals to PO over PC. I'll repeat again. Because of the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB equals to PO over PC. So here PD is the square root of 5 units over PB. Here PB equals to 2 plus 2, that is 4, and it is equal to DO equals to 1 over CB is the missing line segment, so we leave it as it is, and it is equal to PO, it is actually PO equals to 2 units, and PC equals to square root of 5 units plus DC. So in conclusion, I found out that square root of 5 over 4 equals to 1 over CB, that is equal to 2 over square root of 5 plus DC. Here we create the first equation from those two expressions. Here, only to the first equation, square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation, equation number 1, and we get that according to equation number 1, square root of 5 times CB equals to 4. Here we divide this equation, equation number 1, by square root of 5, and we will get that CB equals to 4 over square root of 5 units. Here, CB equals to 4 over square root of 5 units. Here we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. According to the Pythagoras theorem on the right blue triangle, triangle DCB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is dB squared. That is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to DC squared plus CB squared. Okay. Only to the Pythagoras theorem, dB squared equals to DC squared plus CB squared. dB equals to square root of 5, so dB squared is 5, and it is equal to DC is the missing 9 segment, so we leave it as it is, DC squared plus CB squared. CB is 4 over square root of 5, so CB squared is 16 over 5. So in conclusion, I found out that 5 equals to DC squared minus 16 over 5, so we will subtract 16 over 5 from this equation, and we get that 5 minus 16 over 5 equals to DC squared. Here we will multiply 5 by 5 and then we will divide it by 5 in order to have a common factor with this expression, and we get that 5 times 5 is 25 minus 16 over 5. That is equal to DC squared. So here 25 minus 16 is 9. So 9 over 5 equals to DC squared. We take a root out of this equation and we'll get that only to this equation, the left of side DC, it is equal to 3 over square root of 5 units. So here we can write down that DC, the left of side DC of the right triangle DCB, equals to 3 over square root of 5 units. Now it is very easy to find out the area of this blue right triangle, triangle DCB. The area of this blue right triangle DCB will be equal to the base of the triangle that is DC times the height of the base that is CB over 2. So the area of triangle DCB equals to the base of the triangle that is DC times the height of the base that is CB over 2. Repeat again, the area of the right triangle, triangle DCB equals to the base that is DC times the height of the base that is CB over 2. So here DC is 4 over square root of 5 times CB, that is 3 over square root of 5, all divided by 2. So here in the numerator we have 4 times 3 is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. 12 over 2 is 6, and the denominator we left only with 5, so it is 6 over 5. So in conclusion, we found out that the area of the right blue triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. We finished with the second method. In the next step, I will summarize the lecture. Square units. Okay. Repeat again. The area of the right triangle DCB, right blue triangle, equals to either 6 over 5 units, or in terms of numbers, it is 1.2 square units. Okay, so I'll summarize the lecture. We'll start with the first question. So here we have the right triangle, triangle ABC, side AB equals to 8 units, angle ABC equals to 90 degrees, and we have to find out the radius of this circle that is described by triangle ABC, and it is also given us in the question that the length of BC and the length of AC, that is the hypotenuse, are integers. And we want to find out the radius of this circle that is described by triangle ABC. So, first of all, we define side BC as A and side AC, the hypotenuse, as B. Then we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the surface of the perpendiculars. That is to say, BC AC square, this is the square of the hypotenuse, equals to AB square plus BC square. AC is B according to our definition, so AC square is B square, and this is equal to AB square. AB is 8, so AB square is 8 squared, that is 64, plus BC square. BC is A according to our definition, therefore BC square is A square. We subtracted A square from this equation, and we got that B square minus A square equals to 64. We use the algebraic identity that states that B square minus A square equals to B plus A times B minus A. So we substitute B square minus A square by B plus A times B minus A. And according to equation number 1, it is equal to 64. So actually it is given us the question that here AC and BC are integers, and according to our definition, AC equals to B and BC equals to A, therefore A and B are integers. And we also know that A and B are the length of the sides of the right triangle. So A and B as a length, they must be a positive. So according to 1 and 2, we'll get that A and B are positive integers. Okay? That is to say, actually, A and B are natural numbers. Okay, so here, and because of the fact that we know that A and B are positive integers, so A is a positive integer and B is a positive integer. Therefore, B plus A must be also a positive integer, because if we add two positive integers to each other, the result must be a positive integer. But we also know that the hypotenuse B is greater than the perpendicular A, so we can write here that B is greater than A. We subtracted A from this equation and found out that B minus A is a positive number. So, if B minus A is a positive number, and B is integer and A is integer, it means that B minus A must be also a positive integer. Okay, so I found out that B minus A is a positive integer, and B plus A is also a positive integer, and also that B plus A is greater than B minus A. So actually, according to equation number 1, if we multiply B plus A by B minus A, we will get 64. That is to say, we have two positive integers that we will multiply by each other and we will get 64. So what are the possibilities for taking out two positive integers and multiplying one by each other and to receive the result of 64? There are not a lot of possibilities. Here it might be the first number 1 and the second number 2, that is to say b plus a must be 1, might be 1, and b minus a might be 64, and 1 times 64 is 64. And we have another possibility that b plus a is 2 and b minus a is 32. 2 times 32 is 64. The first possibility is that b plus a is 4 and b minus a is 16, and 4 times 16 is 64. And we have another possibility that the first number is 8 and the second number is 8 also, and 8 times 8 is also 64. We have another possibility that the first number is 16 and the second number is 4, and 4 times 16 is also 64. And we have another possibility that the first number is 32 and the second number is 2, and 32 times 2 is 64. And finally, we have the possibility that the first number is 64 and the second number is 1, so, and 64 times 1 is also 64. Okay, so we have here 7 possibilities for the solution of the question. But according to this equation, we know that b plus a, that is the first number, must be greater than b minus a. So b plus a is in the first column, while b minus a in the second column. And we know that the first column, b plus a, must be greater than b minus a. That is to say, the first column must be greater than the second column. Okay? So here we check out if whenever we will see that the first column is greater than the second column, then it is a good possibility. But if we found out that the first column is less than the second column, then it is not a good possibility, because here b plus a must be greater than b minus a. Here 1 is less than 64, therefore it is not a good possibility. 2 is less than 32, therefore it is not a good possibility. 4 is less than 16, that is to say it is not a good possibility. 8 is not greater than 8, that is to say it is not a good possibility. And we know that 16 is greater than 4, that is to say it is a good possibility for the answer to the question. 32 is also greater than 2, that is to say it is a good possibility. And we know 64, that is also greater than 1, therefore it is a good possibility for the question. So we found out that out of 7 options, we left only with 3 possible solutions. The other one are not good because they don't meet this requirement that b plus a is greater than b minus a. In the next step, we will add the two numbers together in order to find out what is the result. So we add b plus a to b minus a. B plus a plus b minus a is b plus b is 2b, and a minus a is 0. So in conclusion, we found out that if we add the two numbers together, we will get 2b, that is an even number. That is to say, if we add the two numbers together, we must get an even number. Otherwise it is not a good answer. If we don't get an even number here by adding the two numbers together, it is not a good solution, because the solution must be, when we add the two numbers together, there must be an even number. Otherwise it is not a good answer, because b plus a must be, b plus a plus b minus a must be an even number. So we add the two numbers together to check if they are even numbers or not. So 16 plus 4 is 20. 20 is an even number, so this is a good solution. And we have the second solution, that 32 plus 2 is 34. 34 is indeed an even number, so it is a good solution. But finally we have also 64 plus 1, that is an odd number, it is not an even number, so we'll cancel this solution. So we left only with two solutions that are possible, either b plus a equals to 16 and b minus a equals to 4, and we have the other solution that b plus a equals to 32 and b minus a equals to 2. Okay? So we write down the two solutions. According to the first solution, b plus a equals to 16 and b minus a equals to 4. And according to the second solution, b plus a equals to 32 and b minus a equals to 2. So here we will add the first equation to the second equation, and we get that b plus b is 2b, a minus a is 0, and 16 plus 4 is 20. So in conclusion, we found out that 2b equals to 20. We divided this equation by 2 and found out that b equals to 10. And according to this equation, b plus a equals to 16. We subtracted b from this equation and found out that a equals to 16 minus b. But we already found out that b equals to 10, so we can substitute b by 10, and we'll get that a equals to 16 minus b, that is 10. 16 minus 10 is 6. So in conclusion, we found out that the first solution to the question is that a equals to 6 and b equals to 10. And according to the second solution, we'll find out the values of a and b here. We'll add the first equation to the second equation, and we get that b plus b is 2b and a minus a is 0. 32 plus 2 is 34. So we got here the equation that 2b equals to 34. We divided this equation by 2 and we got that b equals to 34 over 2 is 17. And according to this equation, b plus a equals to 32. We subtracted b from this equation and found out that a equals to 32 minus b. So, but we already found out that b equals to 17, so we can substitute b by 17. We did it and we got that a equals to 32 minus b, that is 17. That is to say, a equals to 32 minus 17, that is 15. So we found out in conclusion that according to the second solution, a equals to 15 and the hypotenuse b equals to 17. Then I drew the two solutions in this place. According to the first solution, a here it is equal to 6, the hypotenuse AC equals to 10, and AB equals to 8 units. It is given as the question. Inside this right triangle, we have this circle that is described by the right triangle ABC, and we have to find out the radius of this circle that is described by this specific triangle. And according to the second solution, the hypotenuse AC is 17, here BC is 15, and AB is 8 units. It is given as a question. And inside this right triangle, triangle ABC, we have this circle that is described by this right specific triangle, triangle ABC. And our mission is to find out the radius of this circle that is described by this triangle, triangle ABC. Okay, in order to find out the radius of this circle that is described by right triangle, triangle ABC, we will draw a triangle ABC that could be any right triangle. Here, this triangle, triangle ABC, could be any right triangle. And inside this right triangle, we have this circle that is described by the right triangle. And we know that side AB equals to A units, side BC equals to B units, and side AC equals to C units. And we want to find out the radius of this circle that is described by this right triangle, triangle ABC, that could be any triangle. Okay? So, I presented to you the first rule that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, the point of tendency of tangent AB with this circle is point M, the point of tendency of tangent BC with this circle is N, and the point of tendency of tangent AC with this circle is L. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have the radius OM that is drawn to the point of tendency. Therefore, according to rule number 1, tangent AB will be perpendicular to the radius MO, that is to say this angle equals 90 degrees and this angle also equals to 90 degrees. Likewise, we have here the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent BC with this circle, and whenever radius that is drawn to the point of tendency, then tangent BC will be perpendicular to radius NO. So if BC is perpendicular to NO, we get that this angle equals 90 degrees and this angle also equals to 90 degrees. So actually inside quadrilateral MOBN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the fourth angle, that is angle MON. In total, they must be equal to 360 degrees. If we subtract from the equation 270 degrees, we get that the missing angle, this angle MON, equals to 90 degrees. So actually we found out that quadrilateral MOBN, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So quadrilateral MOBN is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other, that is to say MO equals to BN. But MO equals to R, therefore BN also equals to R. According to the sum rule that the opposite sides of a rectangle are equal to each other, we get that MB equals to ON. MB equals to ON, but we already found out that ON equals to R. Therefore, MB must be also equal to R because they are equal to each other. So in conclusion, quadrilateral MOBN, it is not a rectangle but a square. Then we found out the length of line segment AM. AM, from the drawings, is very easy to see that AM equals to AB minus BM. AB is A and BM is R, so in conclusion, AM equals to A minus R. Then we found out the length of line segment NC. From the drawings, it's very easy to see that NC equals to BC minus BN. BC is B, BN is R, so in conclusion, NC equals to B minus R. So in conclusion, we found out that NC equals to B minus R and AM equals to A minus R. Then I presented to you rule number 2 that says that the lengths of two tangents from a common extreme point to a circle are equal. So if we focus on the common extreme point, point A, we have two tangents to this circle, tangent AM and tangent AL. And according to rule number 2, they are equal to each other. That is to say, AM equals to AL. But we have already found out that AM equals to A minus R, therefore AL that is equal to AM must be also equal to A minus R. Then we focus on the common extreme point, point C. From the common extreme point, point C, we have two tangents to this circle, tangent CL, tangent CN, and tangent CL. And according to rule number 2, they must be equal to each other. That is to say, CL equals to CN. But we have already found out that CN equals to B minus R, and CN also equals to CL. Therefore, CL will be also equal to B minus R. So in conclusion, we found out that CL equals to B minus R, and AC and AL also, it is also equal to A minus R. AL equals to A minus R and LC equals to B minus R. So the hypotenuse AC, it is equal to AL plus LC. The hypotenuse AC equals to AL plus LC. AC AL plus LC. AL equals to A minus R. We substitute AL by A minus R. And LC equals to B minus R. So we substitute LC by B minus R, and so we found out that AC equals to A minus R plus B minus R. But according to our definition, AC equals to C. So we substitute AC by C and found out that C equals to A minus R plus B minus R. So C equals to A plus B, minus R plus minus R is minus 2R. So in conclusion, we found out that C equals to A plus B minus 2R. We added 2R to this equation and found out that 2R plus C equals to A plus B. We subtracted C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that the radius of this circle that is described by triangle ABC, that would be any triangle, it is equal to A plus B, that is the sum of the perpendiculars, minus C, that is the hypotenuse, the length of the hypotenuse, over 2. Okay, now we can implement the new formula in our drawing. In our drawing, we have those two right triangles. Inside those two right triangles, we have those two circles, and we want to find out the radius of those two circles that are inscribed by the right triangles according to the new formula. Why? Because of the fact that triangle ABC could be any triangle, and we can use it for those two specific triangles that have two circles that are inside those two triangles. Okay? So according to the new formula, R equals to A plus B minus C over 2. So R, the radius of this circle, will be equal to the sum of its perpendiculars, that is 8 plus 6 is 14, minus the hypotenuse that is 10 over 2. 8 plus 6 is 14, minus 10 is 4, and 4 over 2 is 2. So in conclusion, we found out that the radius of this circle that is described by this specific triangle ABC, it is equal to 2 units. Then we have here this right triangle, and the radius of this triangle will be equal to a plus b minus c over 2. A plus b is the sum of its perpendiculars, that is 8 plus 15, that is 23, minus the hypotenuse, that is 17. 23 minus 17 is 6, and 6 over 2 is 3. So we found out that the radius of this circle is 3 units. So in conclusion, we have two solutions to this question. Either the radius of this circle either equals to 2 units or to 3 units. And this is the answer to the question. Okay, the radius of this circle that is described by the right triangle ABC will be equal to either 2 units or 3 units. We finished with the first question, then I presented to you the second question, and we solved the second question in two different methods. According here in the second question, we have a contour circle. AOB is a contour circle. Side OB equals to 2 units. AD equals to DO. Inside this contour circle, we have the blue right triangle OCB. Angle OCB equals to 90 degrees. And we want to find out the area of the blue right triangle OCB. Okay, so first of all, because of the fact that AOB is a contour circle, this angle equals to 90 degrees. OB is the radius that is 2 units. AO is also the radius that is 2 units. And we know that AO equals to O, AD equals to DO. So if AO equals to X, then DO will be also equal to X. And AO equals to AD plus DO. See here, AO equals to AD plus DO, but if AD is X, then DO must be also equal to X because they are equal to each other. So in conclusion, I found out that X plus X equals to the radius of this circle, the radius of the contour circle, that is 2 units. 2x equals to 2, we divided this equation by 2 and we found out that x equals to 1 unit. Okay, so here AD equals to 1, that is x, and DO, that is x, also equals to 1. Okay, then we completed the contour circle to a circle, and we extended the radius BO by straight line until it touches the circle at point P. O is the center of the circle, P is the point of the circle itself, therefore OP is the radius of the circle, that is 2 units. Then we extended side CD by a straight line until it touches the circle. So we assume that it touches the circle. When we extend side CD by a straight line, we will assume that it touches the circle at this point X, that is not point P. So according to this assumption, we created peripheral angle BCX that is equal to 90 degrees, and we know that PB is the diameter of the circle because it passes through the center of the circle. So we have here peripheral angle BCX that is equal to 90 degrees, and it is not resting on the diameter of the circle. And this is a contradiction, because any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, that is PB. Therefore, peripheral angle BCX, that we assumed that it touches the circle at this point, that is not point P, must merge with point P. Otherwise, we get here peripheral angle that is equal to 90 degrees and it is not resting on the diameter of the circle. That is a contradiction. In order to avoid this contradiction, when we extend side CD by a straight line, the straight line must touch the extended straight line must touch the circle at point B and only at point P. Okay? That is to say, peripheral angle BCX equals to peripheral angle BCP, and point X merge with point P. Okay? Then we have here, we know that PB is the straight line, therefore PB is the diameter of the circle, therefore it is absolutely a straight line, and the sum of the angles on one side of a straight line equals to 180 degrees. So if we focus on this point O, we know that the sum of the angles must be equal to 180 degrees. So here 90 degrees plus the size of this angle must be equal to 180 degrees according to the rule that I mentioned. So this angle must be equal to 90 degrees in order to complete the sum of the angles on the upper side of BP at point O to 180 degrees. This angle must be equal to 90 degrees. So here we have right triangle, triangle POD. We implemented the Pythagoras theorem on the right triangle, triangle POD in order to find out the hypotenuse PD. So in the right triangle, triangle POD, we have here PD square equals to DO square plus BO square. So PD square equals to DO square, DO is 1, so DO square is 1 square, that is 1, plus PO square, PO is 2, so PO square is 2 square, that is 4. So in conclusion, we found out that PD square equals to 1 plus 4, that is 5. We took out of this equation, we found out that PD equals to the square root of 5 units. Then we focus on the right triangle, triangle DBO. And we implemented the Pythagoras theorem in order to find out the length of the hypotenuse DB. In the right triangle DOB, according to the Pythagoras theorem, DB square equals to DO square plus OB square. That is to say, DB square equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus OB square. OB is 2, so OB square is 2 square, that is 4. So in conclusion, we found out that DB square equals to 1 plus 4, that is 5. Here we took out of this equation and found out that the hypotenuse DB equals to the square root of 5 units. Okay? Then we extended line segment AO by straight line until it touches the circle at point Z, and we presented to you rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O inside the circle, of course, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord AZ that intersects with chord CP at point D. Again, chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ equals to CD times DP. Okay, here AD times DZ equals to CP times DD according to rule number 1. AD equals to 1 unit, DZ equals to 1 plus 2, that is 3. CD is the missing line segment, and DP equals to square root of 5 units. Here we got that square root of 3 equals to CD times square root of 5. We divided this equation by square root of 5, and we found out that CD equals to 3 over square root of 5. Here CD equals to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle, triangle CDB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, DB square equals to DC square plus CB square. DB equals to the square root of 5 units, so DB square is 5. DC is 3 over square root of 5, so DC square is 9 over 5, plus CB square is the missing side. So we leave it as it is. Here we subtracted 9/5 from this equation. We found out that 5 minus 9/5 is equals to CB square. We multiplied 5 by 5 and then we divided by 5 in order to have a common factor with this expression, and we found out that 5 times 5 is 25, and 25 minus 9 is 16, so we have 16 over 5 equals to CB square. Here we took out of this equation, we found out that CB equals to the square root of 16, that is 4 over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5. Then Now it is very easy to find out the area of this blue right triangle, triangle DCB. It will be equal to the base of the triangle, that is DC, times the height, that is CB over 2. Again, the base DC times the height DCB over 2. DC is the base times the height of the base, that is CB over 2. DC is 3 over square root of 5 units. CB is 4 over square root of 5 units, all divided by 2. In the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5, that is 5 times 2. So here 12 over 2 is 6, so in the numerator we have 2. And the denominator what is left is only 5. So in conclusion, found out that the area of the blue right triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Here we finished with the first method. Then I presented to you how to find out the area of the blue right triangle, triangle DCB according to the second method. According to the second method, here we know that this angle equals to 90 degrees according to the first method. AD equals to 1 and DO equals also to 1 according to the first method. Then we completed the quarter circle to a semicircle, and we extended the radius BO by straight line until it touches the circle at point P. Then from point we extended side CD by straight line until it touches the circle at point P. And according to the first method, I proved that when we extend side CD by straight line, it must touch the circle at point P and only at point P. Okay? We have already found out that this angle equals to 90 degrees. We have already found out that according to the first method that PB equals to square root of 5 units. And here the hypotenuse OB and the hypotenuse OB equals to square root of 5 units. Then we defined angle DPO as theta. So angle DPO equals to theta. This angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle 280 degrees. This angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. Then we focus on the right triangle PCB. In the right triangle PCB, this angle equals to theta, this angle equals to 90 degrees, and this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle equals to 90 degrees minus theta. Okay? Then we prove that the right triangle POD is similar to the right triangle PCD. Why those two right triangles are similar to each other? First of all, we have those two angles, the right angles, therefore they are equal to each other. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And this angle is the common angle that belongs to both triangles, so this angle equals to itself. So we actually proved that all three angles of the big right triangle PCB can go into all three angles of the small right triangle, triangle POD. Therefore we proved that those two right triangles are similar to each other according to angle similarity rule. Here triangle POD is similar to triangle PCB according to angle similarity rule, and from the fact that they are similar to each other, we conclude that the following relationship exists between their sides, that PD over PB equals to DO over CB equals to PO over PC. Okay, here PD over PB equals to DO over CB, and it is equal to P. It is equal to PO over PC. Okay. PD equals to square root of 5 units. PB equals to 2 plus 2, that is 4. DO equals to 1. CB is the missing line segment, so we leave this it is. PO equals to 2 and PC equals to square root of 5 plus DC. So in conclusion, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus CD. From this long equation, we derived the first equation, the square root of 5 over 4 equals to 1 over CB. We of course multiplied this equation, equation number 1, and we found out that square root of 5 times CB equals to 4. We divided this equation, equation number 1, by the square root of 5, and we found out that CB equals to 4 over square root of 5. Here CB equals to 4 over square root of 5. Then we implemented the Pythagoras theorem on this right triangle, triangle DCB. According to the Pythagoras theorem on this right triangle, triangle DCB, DB square equals to DC square plus CB square. Here DC square, DB square equals to DC square plus CB square. DC is square root of 5, so DB is square root of 5. So DB square is 5. This is the missing side, so we leave it as it is. CB is 3 over square root of 5, so CB is here. CB is 4 over square root of 5, so CB squared is 16 over 5. So if we're going to find out that 5 equals to DC square plus 16 over 5, we subtracted 16 over 5 from this equation, and we found out that 5 minus 16 over 5 equals to DC squared. Here we multiplied 5 by 5, and then we divided it by 5 in order to overcome a factor of this expression. And we found out that 25 minus 16 over 5 equals to DC squared. 25 minus 16 is 9, so in conclusion we found out that 9 over 5 equals to DC squared. We took out of this equation and found out that DC equals to the square root of 3, that is 3, the square root of 9, that is 3, over square root of 5. So here, this equals to 3 over square root of 5. Now, it is very easy to see, to find out the diameter and the area of this blue right triangle, triangle DCB. It is equal to the base of the triangle that is DC times the height of the base that is CB over 2. The area of this right blue triangle DCB equals to the base of the triangle that is DC times the height of the base that is CB over 2. DC equals to 4 over square root of 5. CB equals to 3 over square root of 5, all divided by 2. 3 times 4 is 12, so in the numerator we have 12. In the denominator we have square root of 5 times square root of 5 is 5, times 2. So 12 over 2 is 6. In the denominator we left only with 5. So in conclusion we found out that the area of this right blue triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. So in both methods we arrive to the same answer, that the area of the blue right triangle equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, thank you very much.